What I'd like to talk about next are methods of energy transfer to ideal gases. Now, we're going to talk about some methods of energy transfer in general, which include much more than just these two I'm specifying. But since we're talking about ideal gases, I thought this would be a good time to introduce this. So, there are two ways to transfer energy to gases. And the first one is mechanical work, W. You've seen that before. The other way is heat, Q. Now, mechanical work is what we'll start with. Mechanical work is symbolized by W and is measured in joules, as you already know. But mechanical work is the process of energy transfer done by exerting a force through a displacement parallel to the force. So, an object does not possess work. You don't say an object has work. It can do work, or it can have work done on it. Work is a process. Work is the transfer of energy from one thing to another by exerting a force through a displacement parallel to the force. In thermodynamics, the letter W represents the mechanical work done on a gas. And the reason I have to specify this is because in old formulations, in like very old textbooks, work was considered the work done by a gas instead of the work done on a gas. Nowadays, we want to stress the concept of conservation of energy, so W represents the work done on a gas from here on out. The environment can do work on a gas just by, if you just compress a piston containing a gas, you're doing work on the gas. In this case, positive work is done on the gas and W is positive. On the converse, though, a gas can do work on the environment. In this case, if the gas is doing work on the environment, we say the environment is doing negative work on the gas. In this case, W is negative, and I'll show you some examples and a demo of this specific thing. Now in this demo, I have a cart which has some kinetic energy. So because it has kinetic energy, it can do work. What it does is it hits this block and it exerts a force to the right on the block, and the displacement of the block is to the right, so positive work has been done on the block. By contrast, if you look at the work done on the cart during the collision, the force on the cart is to the left, while the displacement of the cart is to the right. Hence, the block does negative work on the cart. In summary, anytime object A does positive work on object B, then object B does negative work on object A. And this will be important when we talk about work done on the gas by the environment. The symbol W is always work done on the gas. So if the work done on the gas is negative, that's just saying the gas does positive work on something else like the environment. What I've got here in this demo is a gas trapped in a container, and it is an ideal gas. It's monatomic, so it could be best emulated in real life by something like argon, neon, or helium, all of which are monatomic gases, noble gases. So I'm going to show you how there's a couple different ways that I can add energy to this gas. Now, right now you can see the thermometer up here is reading around it's variable a little bit, but it's reading somewhere around 350 in general. What I'm going to do is I'm going to do some work on this gas, some mechanical work, by exerting a force and a displacement in the same direction. Pushing it that way, that little space guy is exerting, doing some work on this. Look what is happening to the temperature of the gas and the internal energy of the gas. Now you may see that those objects are now moving faster. The average kinetic energy of the molecules is greater, and as an ideal gas, the temperature is also greater. Now I'm going to go back. The space guy is still pushing to the right, but the displacement is to the left. The space guy does negative work on the gas, causing it to lose energy. W is negative. Negative work is done on the gas. So now we're back to about 450 degrees. Now the other way that you can add energy to the gas is by adding heat. And the environment can add heat to this by putting something very hot right next to it. For example, a burning gas. By putting this burning gas next to it, I can also add energy to it. Notice that the heat also adds kinetic energy to these molecules. And now they are moving faster, they have higher kinetic energy, and our temperature is also greater. Now, we can also remove heat from the gas by simply taking some ice. And now what's happening is the energy is leaving the gas, heat is leaving the gas and going into the ice, causing the ice's temperature to rise, or it may cause it to just
melt while remaining the same temperature.
So we can have work that is positive, increasing the energy. We can have work that's negative, decreasing the energy. Work represents work on the gas. We can have heat that's positive, adding energy. We can have heat that is negative,
where energy is leaving the gas.
And those are the ways we can add and take away energy from a gas sample.